Hey everybody, today we're going to be talking about conservation of mass. Um, so first of all, let's just kind of go over the conservation of mass equation again. So the conservation of mass equation has two parts. It has the accumulation term and it has the flux term. Accumulation term just tells you how much mass is accumulating within the system over time, and the flux term tells you how much mass is passing through our system boundaries. So in this case, as you can see in this first part, we have kind of like a piping system as such. And we are given the information of V1, V2, A1, A2, A3, and rho. And yeah. So in this case here, the first thing we need is to start giving information. And what we're trying to find is V3 and theta. So then our next step would be to draw the diagram, which I've already done for us. And then the third step we would do, or the following step, would be the assumptions. So in this case, what we're going to assume is we're going to assume that the steady system, steady conditions, which gets rid of this term in our equation. And we're also going to assume that there is no losses due to friction. So you don't have to worry about, in this specific problem, we're not going to worry about the losses generated by flow through a pipe. Yeah. Okay. So the next thing we got to do then is the analysis phase, where we're going to rewrite the equation that we have after making our assumptions. So we have the control surface rho v dA is equal to m dot, which as we know is equal to 0. In this case, the control surface we're going to use is, let's see, I can dot it out. We're going to do this as our control volume, which means our control surface is going to be surface 1, surface 2, surface 3. So when we replug everything back in, then we're going to do, so the integral of control surface 1 would be surface 1, rho 1, v1, dA. Plus surface 2, rho 2, v2 dA, minus surface 3, rho 3, v3 dA is equal to 0, which ends up giving us rho 1, v1 dA, or sorry, not dA, a1 in the x direction, plus rho 2, v2, a2 in the y direction, minus rho 3, v3, a3 in the n direction, which we don't know. So bring this part over to the side, we end up, yeah, we'll just do it like this. So that's what we end up having, right? This portion right there. So then now with this, we're assuming this is all the same liquid. So I guess we should say rho is constant. So we're saying it's incompressible as well, so there's no compressibility effects. So our rho's will cancel out. And then what we can notice here is that this first term and the second term are independent of one another. It's in the x direction and the y direction. So then our summation, or this value here, is actually the magnitude of this term over here. So if we were to write that, we're first actually going to bring the V3 over. So you'll have this over, sorry, not V3, A3 over. We'll get rid of the A3 there. So then you'll have V3 is equal to the square root of V1 A1 over A3 squared plus V2 A2 over A3 squared. Okay, so this gives us our V3. So then if we are now trying to find our theta value, which is that theta there, we're going to take our x component, we're going to inverse tangent our y component over our x component, which our y component in this case is equal to V1 A1 over A3, and we're going to divide that by V2 A2 over A3. And this should give you what the theta value is. Anyways, I hope this was informative and that this kind of helps you understand how to approach a conservation of mass problem a little bit clearer. I chose to do this symbolically so that could be applied to multiple scenarios rather than just the specific problem that we were considering. Okay, well, thanks everybody. Until next time.